Okay, I'm now going to go over the parts that were attempted in section B. Okay, B. Right, so here we are at section B. The first question is actually quite a straightforward one. It's about energy changes and momentum. So, if we have a look, we have an arrangement used to test golf club heads. So as you can see, you've got a pivot here, and as this club head drops, it hits the ball. So question number 1, describe the energy changes that take place in the club head the instant the club is released up here until the club head and ball separate. So presumably it hits the ball and then the ball goes that way, and we don't know what happens to the club yet. Okay, so the energy changes are pretty clear. We start off with gravitational. Okay, gravitational of the club head to kinetic of the ball, and if you want to say heat, you can also say, but use internal energy. Don't use the word heat anymore. Internal energy of the ball. Okay, and that's pretty much it. You could also say some of the kinetic energy would stay, because of course this might rebound, you never know, so you could infer that there is some kinetic energy in the club head as well. But the 2 marks are pretty self-explanatory. They're for the first 2. Okay, so now we're going to try to work out the maximum speed of the club head when the height is 0.85. Height is 0.85 because it comes down and all that gravitational energy becomes kinetic. So we have GPE equals kinetic. So substituting our relationships, mgh equals a half mv squared. Mass is on both sides. So 10 times 0.85 equals a half v squared. Okay, so if we rearrange, we will end up with 8.5, that becomes 8.5 times 2. Okay, and then we square root it and we end up with v equals 4.1 ms minus 2. Right, so we go on to the next part. The diagram shows deformation of a golf ball as they collide. Explain how increasing the deformation of the club head increases the speed. So this is a question about time, because if you increase the deformation, basically it takes longer, it sticks around, changing the shape of the golf head. So therefore the time of contact increases. And if we're talking about times and collisions, we're talking about impulse. Ft equals the change of momentum, which is the momentum after minus the momentum before. So what happens if we increase the impulse? If this goes up, okay, then the velocity, the new velocity, if we rearrange this formula, it will look like this. mv equals ft plus mu, and if you increase this, then this must increase as well. So explain how increasing the deformation of the club head may be expected to increase the speed. By increasing the deformation, we are increasing the time, which increases the impulse, so therefore makes the change of momentum bigger, and therefore increases that velocity. Okay, so let's try this section. In a different experimental arrangement, the club head is in contact with the ball for a time of 220 microseconds. The club head has a mass of 0.17 kilograms. The ball has a mass of 0.045 kilograms. At the moment of contact, the ball is at rest, it's another velocity there, and the club head is moving at a speed of 38. The ball moves off with an initial speed of 63 meters per second. So this is a standard momentum and a conservation of momentum and impulse question. Okay, so hang on, do it with my pens. Calculate the average force acting on the ball. Well, force equals the change in momentum, which is mv minus mu, over the time, which is equal, we're considering the ball, okay, so just the ball. You can't mix what's going on with the club head and the ball, so you have to be very, very clear. The ball has an initial speed of 63, okay, and initially it was at rest. Okay, so these are our two velocities. We have the mass of the ball, 0.045, 63, that's the velocity after the collision, minus 0, which is its velocity before the collision, over the time, which is 220 times 10 to the minus 6. Okay, look at my answers. You should get an answer of 1.3 times 10 to the 4 newtons. Okay. Now, question, state the average force acting on the club head, because we've worked out the force acting on the ball. So this is kind of a sneaky question. If you know the force acting on the ball, what is the force acting on the club head? Well, this is Newton's third law. Action and reaction are equal and opposite. So therefore, you should have exactly the same force. If it's 1.3 times 10 to the 4 newtons on the ball, then the ball must be applying the same force on the club head. Okay. Question 3. Calculate the speed of the club head at the instant that it loses contact with the ball. Okay. We have conservation of momentum. It's probably the easiest way to calculate this formula. So you have your momentum before, which is the mass of the club head times the velocity of the club head before, plus the mass of the ball times the velocity of the ball before. Those must be, this is before, and then after, the mass of the club head plus the mass of the ball, the mass, velocity of the ball after. Okay, so you just substitute your values in there, remembering that that this was 0. Okay, so we have right, mass 0.17 times the velocity of the club head, 0.38, plus 0, because this was 0, so therefore the velocity of the ball before was 0. Okay, equals 0.17 times v, which is what we're trying to find out, the velocity of the club head after the collision, plus 0.045 times 63 after the collision. And you work that all out and you rearrange, and you should get a value for the velocity of the club head of 21 meters per second. Right, so part 2. Here we have our binding energy graph, which you should be familiar with. And the first question, our definitions. Define what is meant by nuclear binding energy. And that's just something you're going to have to learn off by heart. Nuclear binding energy, there are many ways of interpreting it, but this is probably the quickest. Energy released when nucleus formed from component individual nucleons. Individual nucleons. And by energy released or energy given off, when nucleus formed from a component individual nucleons. Anything that kind of shows that you understand that there is a difference in mass, and that mass defect equates to energy. Okay, but I think we're going to deal with definitions differently when we get back to school. To label with letter S the region on the graph when nuclei are most stable. So you should remember that it's the highest point, the part with the greatest binding energy per nucleon, because it's the least likely to happen. So you have to find which is the highest point, which is actually up there, okay, and single it out quite specifically, which would be the iron nucleus, although you don't need to say that, it's good to know. Okay, iron is the most stable. Okay, so now part 2. This question is really nice because it really gets to the root of what binding energy is. We have 2 nuclei, or 2 hydrogen nuclei, binding to make a single helium, which basically means that there are 2 nucleons, okay, but there's 2 atoms, so therefore we're using 4 nucleons. And because it's hydrogen, how much energy do we need per nucleon? Well, for that we need to look on the graph. And if you look up hydrogen on the graph, you'll find that it's approximately 1.1 mega evolts, okay? But that's for 1 nucleon. It's 1.1 mega evolts per nucleon. So the amount of energy actually available is 4 times 1.1 mega evolts, which is equal to 4.4. Okay, now you bring those together and you make a helium nucleus. Now helium is 4,2, and the binding energy per nucleon for helium, if you look it up, is about 7.1. Now it's 7.1 per nucleon. How many nucleons do we have? We have 4. So the total binding energy would be times 4. Okay, which would give us 28.4 evolts. So, how much energy is released? Well, the amount of energy that is released is the amount of energy available subtracted from the amount that you had in the first place. So, the binding energy would be, or the binding energy released would be 28.4 minus 4.4 mega evolts, which gives us 24 mega evolts. Okay, so now we need to complete these. We have one nuclear reaction where hydrogen 2 fuses to produce hydrogen 3, and then we have a second one where the tritium, the hydrogen 3, undergoes beta decay, okay, which is that second one. So let's look at the first one. We have 2, 1, 2, 1. So here we basically have 1 left over. If we add up 3 plus 1 will give us the 4 that we had in the first place. Oops. And then the same here, we have 2, so this must be 1. And basically, if we look at this, we can see that it's a proton that's given off. Or you could say a hydrogen nucleus, because it's a very simple hydrogen nucleus. Next step, this hydrogen 3 decays to give us helium. Well, you know this is going to be 2 because alpha particles or helium nuclei are 2, and that you need to know. And if you have 2 there, we somehow or other need to compensate for that by having a -1, whereas a 0 is on the top to balance the 3 out. So a -1, well, that's a beta. You can write a beta, or you can write an electron. That's fine. Okay, or a beta. And because this is beta decay, you know that you have an uncharged neutrino which has no particulate nature. Okay, so you have helium, an electron or a beta particle, and a neutrino. And now part 2, explain which of these reactions is more likely to occur at high temperatures. Well, this is a very sneaky question because you know that decay, natural random decay, is completely unaffected by temperature. Okay, so what is this question about? If you have a high temperature, there is one thing that would happen. Any particles that happen to be free moving under Brownian motion, or moving under any kind of kinetic theory motion, will be affected by temperature. The kinetic energy of these particles will increase with temperature. If the kinetic energy of the particles that are colliding increases, then the collisions will be greater. There will be more collisions and faster collisions, so it will be more likely to happen. So the answer is that the first reaction is the one that's more likely to happen because it's an absorption, it's a collision between two particles that are moving freely. The second one, which is a decay, will be completely unaffected, okay, because the decay is spontaneous. So this one would be unaffected. Okay, here we have quite a straightforward question on simple harmonic motion. We have a time displacement graph, or displacement time graph, say, and you need to find the amplitude. The amplitude is simply a reading of the distance graph. Look, that maximum displacement, which is about 32 millimeters. Okay, and you can express that as meters or millimeters. Question 2, state the frequency of the oscillation. If I make this smaller so we can see, we have time on the x-axis, and as you know, frequency is 1 over the period, and the period appears to be, if we look from there to there, that's the period. Oops, gone a bit too far. Okay, the period is here. Okay, so we have about 160, 1 over 160. But wait, let's have a look at the units. Milliseconds times 10 to the minus 3. Okay. It's difficult doing this when it's spread out like this. Okay, so if we work that out, we will end up with a frequency of approximately 6.2 hertz. And that's that question. Determine the maximum speed of the object. So now we're going to be using some equations. You can either use the graph and look at some gradients, because of course a displacement time graph, the gradients are, the gradient of a displacement time graph will give you velocity, or you can use some equation of motion relationships. We're talking about the maximum velocity, not the velocity in general, just the maximum. And we know that V equals omega x naught, maximum. Okay, so how do we find omega, or the angular velocity? The angular velocity is 2 pi over t, which is equal to 2 pi times the frequency. Actually, you can just use the previous answer because it's 1 over 2. Okay, and that gives us an angular velocity of 39 radians per second. And from this relationship here now, we just multiply the angular velocity, 39, times the maximum, which was 32. This was the amplitude, times 10 to the minus 3. And you should give that gives you an answer of approximately 1.3 meters per second. In the same way, you can work out acceleration. Acceleration, max, acceleration at that particular point, I don't mean max. Okay, just acceleration, equals minus omega squared x. And we know the time. So if you go back to the graph, okay, and you have a look, and if you find at that point 140 times 10 to the minus 3, you should find an x of approximately a displacement minus 24 millimeters. Okay, so you find that value on the y-axis. Once you know that that's, you use your previously calculated value of angular velocity to give you minus 39 squared times minus 24 times 10 to the minus 3, always remembering the units, and you should get an acceleration of 36.5 ms to the minus 2. Okay. Okay, so in this one, we need to plot the kinetic energy of an object over time. Now, kinetic energy, half mv squared, we need to think about what's happening with velocity. We also need to remember that kinetic energy is a scalar, so it will be positive all the time. So where on this graph is velocity a max? Because that will give us our points where we have a maximum kinetic energy. Well, it will be where the gradient is at its highest. Okay, so each and every one of these points, we will have a peak. Okay, in our graph there. Okay, similarly, we can find the points where kinetic energy is going to be at a minimum by working out where v is 0. So if we look at the gradients, we can see that here the velocities are 0 because the gradients are 0. So we have some points there, there, and there where we're going to have naught. So what we have to do now is, in the same way it's a curve, we have to follow. I'm going to try and do this, which is tricky with this app, right? Go up, okay, and then once again here we have 0 and it goes down, and then 0 up, then down, and then up, then down. Okay, so what you've got are peaks which show twice the frequency, okay, because it's almost like a double up. They're positive and they follow the relationship with velocity. Okay, this is another definition question. Electric field strength. And the definition for electric field strength is the force per unit charge. Okay, that's 1 mark on a positive test charge, on a positive test charge. Okay. Part B. Diagram shows a pair of horizontal metal plates. Electrons can be deflected vertically. So the question asks, if you have an electron positioned between the plates, what polarity, that means what charge on each plate, would make the electron accelerate upwards? Well, it will accelerate upwards if there is a force of attraction, and because the electron is negative, it must be accelerating towards a positive plate, and this must be a negative plate. Okay, draw the shape and direction of the electric field between the plates on the diagram. Now, the electric field between uniform plates, you need to know this off by heart, these are straight lines. Okay, so you should have equally distant or equidistant straight lines, but note the direction is the direction of the force that would be experienced if a positive charge was in the field. And if a positive charge is in the field, it would be pulled downwards. So the arrows point downwards. Okay, so here we have calculate force on an electron between the plates, and if we think force per unit charge is the electric field strength. So remember, by definition, electric field strength is force per unit charge, so we can translate this to a relationship, okay? And the force then will be equal to the electric field strength, which is 2.5 times 10 to the 3, times Q, which in this case is the charge on an electron, which is 1.6 times 10 to the minus 19. Okay, and that gives you 4 times 10 to the minus 16 newtons. Okay, now we have another question. We've got two isolated electrons, 1, 2, and of course they are initially at rest in a vacuum. But of course, being both electrons, they are going to repel. The initial separation is 5 times 10 to the minus 3 meters. Right, so we'll change that into SI units now. Show that the initial electric force acting on each electron is approximately 9 times 10 to the minus 24. Well, for that, we need our Coulomb's law relationship, which is F equals our constant Q1, Q2 over R squared, or distance squared. Now K, you can look that up in the data sheet, but that would give us Q, the same electronic charge, it's the charge on an electron, so we're looking at the electronic charge squared. So we have 8.99, the Coulomb constant, times 10 to the minus 9, times 1.6 times 10 to the minus 19. Oops, I don't know if I've written 19. But squared, because we have two of them. We have that one and that one. Okay? And then all of that divided by 5 times 10 to the minus 3 squared again. And that would give us an answer of 9.2 times 10 to the minus 24 newtons. Part 2. Calculate the initial acceleration of one electron due to the force. Again, just using the straightforward relationship, force equals mass times acceleration. Just need to work out or find, the mass of an electron, but this is in the constant sheet. So the acceleration will be the force from the previous question, 9.2 times 10 to the minus 24 over, okay, and it's equal to 9.1 times 10 to the minus 31, and that gives us a value of approximately 1 times 10 to the 7 meters per second. Oops, squared, because it's acceleration. Ding. Now, continuing with the same question, we have two electrons that are repelling, okay, so they experience a force, and because they experience a force, there is an initial acceleration. So we're discussing the motion of one electron after it begins to move. As it accelerates, the distance increases. So if the distance between the two charges increases, then the force will start to decrease. Okay, and if the force starts to decrease, then the acceleration would be less until there is no more force, as it's beyond the field. And because it's in a vacuum, there's no air resistance, etc. So it will reach constant speed. Okay, so you've got 3 marks there, and just to try and highlight them, this would be 1, where there's no more force, you have constant speed. But then you have initial acceleration, and then what happens as the distance increases, the force starts to decrease, and then you get less acceleration. Okay, and then diagram Y, as seen from X at one instant, Y is moving into the plane, so it's moving down into the paper. Draw on the diagram the shape and direction of the magnetic field produced by Y. The magnetic field produced by Y, if you remember using the corkscrew rule, where you had your hand, it's a very bad drawing of it. Okay, if your thumb shows the direction that the current is flowing, which in this case would be into the paper, if you take your left hand and you point your thumb at Y into the paper, the concentric field, magnetic field lines should follow the direction of your fingers, which are anti-clockwise. You get credit for showing a minimum of 2 lines.